Just like feel free to stop me in case you have any questions. Also, like just interrupt me in case there's some issue with the slides or if my voice is not clear. So today I'll be talking about some of my recent research work on the 2H connected subgraph problem. This is joint work with Sylvia Boyd from University of Ottawa, Joseph Cherian, Robert Cummings, Logan Kraut, and Lou Wong from U Waterloo, and Sultan Sigeti from Grenoble in France. The problem that we consider today is the 2H connected multi-subgraph problem. In this, we are given an undirected complete graph, G bar. The vertex set is V bar and the edge set is E bar. And this graph is on n vertices, it contains n vertices. And we are given a metric cost function C. Yeah, so you guys have already, like, just to make it clear, metric means the cost of any edge CUV is at most CUV UW plus CWV. So this is the triangle inequality. That's what a cost function being metric means. And our goal is to find a 2H connected spanning multi-subgraph H of minimum cost, where the cost of H is defined as the sum of costs of edges in H. Okay, and here we count multiplicities. And let me focus on the highlighted, the colored portions. Here, 2H connected means in this subgraph, you can go between any pair of vertices in two distinct ways. There are two edge disjoint paths between any pair of vertices. Spanning means the induced subgraph spans all the vertices. And I use the word multi. What it means here is that I'm allowed to use multiple copies of the same edge. So that is allowed. This is similar to what we see for TSP. We'll come to that in a bit. And just as an example, let's say if we have K4 with these costs, and so one possible feasible solution for the problem is this triangle and these two parallel edges. Okay, it's easy to see that it's 2H connected, spanning, and we also have like two copies of the same edge. And the cost of this subgraph is 90. And I think I've found the optimal solution for this instance, and I think it's shown here. This is like, yeah, this one has cost 80. Any questions regarding like the problem formulation? Let me make a few quick remarks. So this problem 2 ECM, which I described in the previous slide, this is NP hard. And there's a more well-known version, there's a more well-known network design problem called the traveling salesman problem. This is basically like 2 ECM plus the Eulerian property. And what Eulerian property here means is that you want even degree at all vertices. Okay. And this is a very closely related problem. We'll keep mentioning TSP many times throughout the talk. And there's also a strict version called 2 ECS. In this, we have a graph G bar with vertex at V prime and edge at E prime. And observe that like E prime need not be like, G prime need not be like a complete graph. And we are given non-negative cost C on the edge set. And here I don't impose that the cost function be a metric. Okay? And the goal here is to find a 2H connected spanning subgraph, not a multi-subgraph, a strict subgraph of minimum cost. So you're allowed to use each edge at most once. So usually, just a quick remark here, it's that the techniques and lower bound results are very different for each of these these two variants. Okay. Sometimes there's an overlap, but often it is the case that like the results are incomparable. Yeah. Because this is 2ECM is a NP-hard problem, we want to design approximation algorithms for this. So here's the integer linear program that models 2ECM. The objective function is simply the summation of C times XC over all edges. And here, XC denotes the number of copies of E that we want to include in our solution. And the constraints X of delta S at least 2, these are like you might have seen these before. They're mostly like called subtour elimination constraints. But because we are not really talking about tours right now, I'll also call them like just like 2H cut constraints. Okay. 2H connectivity constraints. Okay. And there's an integrality restriction on XC. So this is the IP for this problem. Now, if we want to obtain a linear relaxation for this problem, then we drop these integrality constraints. So by dropping this, we get a valid relaxation for the linear relaxation for the problem. And whatever is the solution objective value coming from this LP, it's a lower bound on the optimal value for 2ECM. So let's say I drop this constraint, then I get 2ECM LP. And there's an interesting property called as the parsimonious property. It says that for such network design problems, whenever you have like a bunch of cut constraints, some sort of connectivity requirements, we can actually assume that the degree of a vertex is in this fractional solution is as small as it possibly can be without violating feasibility. So what it means in this context is that we can include constraints X of delta V equal to 2 for all V in V bar, and the LP value won't go up. So in some sense, like we can add more structure to our fractional solutions by including this constraint, and we won't change the objective value, like the LP value will remain the same. And this is due to Gomans and Birchmarsh. From 93. Yeah. And as you can see, like if you were to stare at this LP, like it is the well-known the subtour LP for TSP. This is a very interesting connection like between these two problems. What it is saying is that in a fractional sense, both the problems have the same linear relaxation. Any questions so far? Okay. Okay. Let's use a special like letter to denote this this polytope, this subtour polytope. So it is the collection of all vectors, non-negative vectors, such that the fractional degree is 2 at each vertex, and the X mass on crossing any cut is at least 2. Okay? It's the same constraints, just like just packaged in a nicer way, in a compact way here. Okay? And we'll denote by LP opt, we denote the optimal value of solving this linear program, which is minimize C transpose X subject to X and P. So this is a lower bound on the optimal solution value. So I've just like said this explicitly here. So LP opt lower bounds the optimal solution for 2ECM. And because TSP is like 2 ECM plus the Eulerian property, the optimal solution for TSP is no lesser than the optimal solution for 2 ECM. And this is a very well-known result, which shows that the integrality gap of this polytope is at most 3 halves. Right? This result is due to Wolsey. So it's basically a polyhedral analysis of Christofides' algorithm, and this is from 1980. Okay? And so this shows that the integrality gap of if I were to denote integrality gap of 2 ECM with alpha 2 ECM with this symbol, then it's saying that it's at most 3 halves. There are numerous results. These problems have been like intensively studied, so there's a lot of literature in this field. I won't be like listing all these results, but there's some like there's some recent exciting progress. Just at the beginning of this month, Anna Karlin, Klein, and Ovesh Garan, Shayan Ovesh Garan, they announced a better than 3 halves approximation for TSP. Yeah. And observe that, note that there's a caveat here. This result is with respect to the integer optimum. So what this means is that they produce an algorithmic solution. They produce a TSP solution whose cost is strictly less than 3 halves times opt for TSP. Okay? So still like the 3 halves bound shown by Wolsey is still the best known bound on the integrality gap for the general case. Okay. So as I said, let me just go back to this slide quickly. It's a very famous, there's a very famous conjecture in our field, which says that the integrality gap of subtour polytope is at most 4/3. Right? So we are currently at 3 halves, and the conjectured bound is 4/3. And it's a very notorious problem. It's very hard to make progress on this because we only saw like progress on this problem very recently, like after almost like 4 decades. And so people have been considering special cases of this problem so that they can make some progress and like learn more about this problem. And one of the one way of restricting the problem is to consider, say, bounded degree graphs, or maybe consider planar graphs, or maybe assume that the cost function is a graphic metric. It's a special kind of a metric, or maybe it is a metric which is induced by node weights. What I mean by that is there are a bunch of node weights on, so each node comes with a weight, and the cost of an edge is equal to the sum of weights on the nodes that it sees. Okay? So people have considered such special metrics and tried to give better than 3 halves approximations for such cases. In this talk, we'll take a different direction. We'll work with like a different class of instances. These are called as half integral instances. This is what appears in the title of the talk. So an instance G bar comma C of 2 ECM, we'll call this as a half integral instance. If you look at an optimal solution for the 2 ECM LP or the subtour LP, they are the same thing. And if you look at an optimal value, optimal solution, extreme point solution, X, and if this X is half integral, i.e. 2 times XC is integral for all edges, then I say that this instance is half integral. So it's not like a explicit classification of an instance as a half integral instance. It's more like you solve an LP, and if the result of this LP is a half integral solution, then such instances are called half integral instances. And the reason these kind of instances have gained popularity is due to a conjecture by Schallekamp, Williamson, and Van Zylen from 2014, which says that the integrality gap of subtour LP is attained on half integral instances. So if this conjecture is true, then to prove the 4/3 conjecture, it suffices to just focus on half integral instances and prove results for that, for such instances. And again, note here that I wrote subtour LP in pink and not like 2ECM LP. So because I mean to say that this conjecture is for TSP, right? Even though the fractional relaxations are the same, the integral versions of 2ECM and TSP are different problems. So the integrality gaps for each of these problems could potentially be different. Let me mention some relevant results that are known for such instances. So in almost 2 decades, more than 2 decades ago, Carr and Ravi showed that for 2ECM LP, the integrality gap of 2ECM LP is at most 4/3. So what Carr and Ravi showed is like they gave a constructive algorithm, but this is not polytime. And so essentially this shows that alpha of 2ECM with respect to half integral instances is at most 4/3. And more recently, like Carlin, Klein, and Oves-Garan, this result appeared in Stock 2020, but the paper was published on arXiv like almost a year ago. What they showed is that for TSP on half integral instances, the integrality gap is actually bounded away from 3/2. So this is evidence that maybe the actual integrality gap of for TSP could potentially be less than 3/2. And what they do here is they give a randomized approximation algorithm for this. And again, this actually implies that the integrality gap of TSP on half integral instances is strictly less than 3/2. Yeah. And we already know of examples where half integral instances where the integrality gap is at least 4/3. So the true number lies somewhere between these two bounds. Yeah. Any questions so far? Our main result in this work is the following. So if you're given a optimal half integral solution X to an instance of 2ECM, then in order n² time, in quadratic time, we can compute a 2H connected spanning multi-subgraph of G bar with cost at most 4/3 times C transpose H. So basically it's the integrality gap result that I showed here. This is due to Carr and Ravi. We basically give an algorithmic version of this result. That's our main contribution in this work. And this is, yeah. Before like delving into the proof of our main theorem, let me motivate why we should study such instances in more detail. Like it shouldn't just be based on like a conjecture that half integral instances are the most general and are the hardest instances. There should be like some more, it deserves some more motivation. So here's a proposition by Carr and Vempala from 2004. What they show is that the integrality gap of 2ECM LP is at most alpha. Let's say if you want to prove this statement, if you want to bound the integrality gap for 2ECM, then it suffices to show that for any positive integer k that is at least 2, and any 2k regular 2kh connected multigraph G if you consider the uniform vector, where I place a mass of alpha over k on all edges in this graph G, this vector, this uniform vector, dominates a convex combination of incidence vectors of 2H connected spanning multi-subgraphs of G. Here, by dominates, I mean that it is coordinate-wise greater than or equal to. I'll come to this in some more detail, like with a specific example in the next slide. But the main idea here is that this gives us like a more combinatorial problem to work with, some very really structured graphs, these graphs which are like 2K regular and 2KH connected. And we want to just work with that and like prove certain properties. And that is sufficient to show that the integrality gap of a certain LP is bounded. And let me talk about how this particular proposition is relevant to our discussion. Okay? So I'll focus on half integral instances now. So what we do is we take a half integral point X, and then we define this graph G that is induced by 2 times X. So observe that 2 times X is integral. So what we can do is we can construct this graph G, which has the same vertex set as G bar. And the edge set E is defined as follows. We take exactly 2 times XC copies of an edge E in E bar. And observe that because the degree constraints are satisfied by X, X of delta V is exactly 2, this graph G is 4 regular. And because the subtour constraints are satisfied by X, we get that G is 4H connected. And this is the result from Carr and Ravi's paper from 2 decades ago. What they show is that if you're given a 4 regular 4H connected multigraph G and an arbitrary edge in capital E, an arbitrary edge little e, then there exists a finite collection H1 through HR of 2H connected spanning subgraphs of G minus E. So all these subgraphs avoid the edge E. And there exists some non-negative coefficients mu1 through mu r whose sum is 1. So I like they form a convex combination. And we have that the vector 2/3 times the almost uniform vector where you put 2/3 mass on every edge in capital E, but not on little e. This can be expressed as a convex combination of the incidence vectors of these 2H connected subgraphs. And here, like I'm doing a bit of an abuse of notation. Here, chi of H means chi of E of HI. I won't be writing E of HI just to be like terse. And the underlying graph will usually be clear from the context. And let me also like focus on this colored word. I clearly say subgraphs. What I mean here is that I want these subgraphs H1 through HR. I want none of them to use more than 1 copy of an edge in G. Okay? So they are avoiding the edge E, and they use at most 1 copy of each edge in G. However, it is okay for H to have multi-edges. And the H can have, any of these HIs can have multi-edges as long as they come from distinct multi-edges in G. So if G had, say, 2 parallel arcs, and if any of the HIs wants to use these 2 parallel edges, then it is okay, as long as you use like 1 copy of each of these. Any questions so far? Like this is a good time to take a break and ask questions. Okay. Because we are like building upon the work of Carr and Ravi, we are mainly like simplifying their proof and also giving an approximation algorithm for the result, it's a good idea to just like go through the high level proof strategy that they use. So we are given 4 regular 4-edge connected multigraph. So we are in this setting, and we have an arbitrary edge E. And our goal is to express this almost uniform vector shown in green as a convex combination of 2-edge connected subgraphs of G. And their proof is inductive, and it has 2 cases. The first case is when this designated edge E belongs to a non-trivial tight cut delta S, which I've shown here in picture. So let's say there's a tight cut, which has exactly 4 edges. And one of them is E, and there are 3 other green edges. And the other case is when case 1 does not happen, which means if there is any non-trivial cut which contains the edge E, then it is not tight. What this means is that there are at least 5 other edges across this cut. Observe that the graph G is Eulerian, so all the cuts have even number of edges. So let me elaborate more on these 2 cases. So in case 1 of Kar and Ravi, this is the easier case in their paper. So here we have a tight cut that contains the edge E and 3 other edges F, G, and H. So what we do here is we obtain 2 smaller instances. In the left instance, we contract the right shore V minus S to a singleton vertex S bar. And on the right subinstance, what we do is we contract the left shore to a single vertex little s. We just give new labels to these edges, but these are the same edges. It's just the same edges, which now have like a new endpoint and a new identified vertex as an endpoint. And we use induction hypothesis to obtain convex combinations for each of these 2 smaller instances. So in this case, we get a convex combination for 2/3 times the incidence vector for all the edges in G1, the ones that you see in this part and these 4 edges, but without the edge E1. And we do the same for the other right subinstance. And to obtain a convex combination for the original graph G, we just glue these 2 solutions together. So what I mean by gluing is that there's a consistent way of just merging these two convex combinations. And there's a reason why that happens. So if you look at this vector, 2/3 times this incidence vector of all edges but little e1, observe that you have 0 mass here, and you have 2/3 on each of these edges, which means in total, the mass at the mass in delta S is exactly 2. And we know that like if we are trying to find a 2-edge connected subgraph, then it must be the case that you must use at least 2 of the green edges, because you're not allowed to use the designated edge, which is shown in pink when you're solving the subinstance. And because the fractional mass is exactly 2, it must be the case that every subgraph in this convex combination uses exactly 2 edges. So they either use F1G1 or F1H1 or G1H1. In fact, we can show with some simple arithmetic that each of these convex combinations, each of these combinations happen with weight 1/3. And the same thing happens on the right-hand side, where you see that like F2G2 is used 1/3 of the times, F2H2 is used 1/3 of the times, and G2H2 is used 1/3 of the times. So you can just take these convex combinations and glue them together. The second case from Kar and Ravi is a bit more technical. So I won't be explaining like the technical details. I'm just going to give like some sort of a high-level picture. We'll be seeing more details when we talk about our simplification of the proof. So in this case, we have that G has non-trivial typeface that contain the edge P. They apply two distinct splitting of operations. I'd like to highlight that in their paper, they don't mention the term splitting off, but essentially this is what they're doing. Okay. So they apply two distinct splitting of operations and they obtain two subinstances. So the way these splitting of operations work is that like a few edges are dropped and some dummy edges are added. Right? So these subinstances are G1 and G2 are very different from like the ones that you see here. Here, there's like a clear association between this edge set and this edge set. But that need not be the case when you move to these split graphs. Most of the graph remains the same, but there are some like new edges, and some of the old edges a few of the old edges have been deleted. We apply induction and we obtain convex combinations for these edge sets, for these uniform vectors. And we do the same on the right-hand side. And then because these graphs were obtained by doing some sort of non-trivial operations, these splitting of operations on the original graph, the solution that you obtain here need not like directly translate to your original graph. So we have to lift these solutions back to the original graph. And that's what this lifting operation is. And we do it for both the subinstances. And we merge, now we combine these two convex combinations to obtain the convex combination for G. And here I would like to highlight that just a simple average works for, is sufficient. Okay. Now we mentioned like, let's see, like we make some simplifications for Karen-Ravi's proof. Again, recall that they didn't give a polytime algorithm. So we are trying to design a polytime algorithm for the result. So we need to make some simplifications so that the algorithm becomes polytime. Our first idea is that we get rid of the gluing step. So recall that gluing step is case 1, and this is the easier case, but we get rid of it because it has its own challenges for like designing a polytime algorithm for this gluing step. But yeah, so we get rid of this. The advantage here is that we unify the analysis by doing this. And what we do is we handle all remaining cases that arise by an extension of Loage's splitting off theorem. And this is due to Bang Jensen, Gabo, Jordan, and Zigati. And this is like one of the hammers that we use in some sense, like that's how you can put it. Right. So the result that we prove, theorem 3, is the following. So given a regular 4-edge connected multigraph G and a designated edge E and an arbitrary cost function C. So observe that the cost can be anything, like they can be negative as well. Okay. Then in order n squared time, in quadratic time, we can find a 2-edge connected spanning subgraph H of G minus E that has cost at most 2/3 the cost of G minus E. Okay. So essentially what this theorem is saying is that there is a polytime algorithm to obtain a 2-edge connected subgraph, which beats the average. Okay. And let me mention this again, that this is a subgraph. So what this means is that like you're allowed to use at most one copy of each edge in G. But multi-edges are allowed as long as they come from distinct copies of multi-edges in G minus E. Because like we'll be using some technical tools, let me go through a few preliminaries on splitting of operation. So what is a splitting of operation? Let's say we have a multigraph G and we have 2 edges, SV and VT, that share an endpoint V. Okay. So the graph GS, T, GST, which is obtained by splitting off this edge pair SV, VT at V, is simply this graph. You include the edge ST and you delete the edges SV and VT. So pictorially, what's happening is we just shortcut from S to T, and we delete these two edges. And we also have this operation of a complete splitting at V. In this, we make a further assumption that this vertex V, this special vertex V, has even degree. And complete splitting is at V is defined as like a sequence of degree V over 2 splitting off operations at V. So each time you're splitting off a pair of edges, and after you perform so many splitting off operations, your vertex V has degree 0. So at the end, degree V becomes 0. It is customary to just like delete V then after a complete splitting has been applied. Now let's talk about admissible pairs. So in this, we need this definition. Lambda h of x comma y, I define this as the size of a minimum xy cut in H. And so let's say so now I define what an admissible pair is. Let K be an integer, and let's say we have a multigraph G where the vertex set is capital V plus there's this special vertex B. And suppose that for all pairs of vertices in this capital V, I don't really care about little v. Let's say the edge connectivity is at least K. Then let's say there's an edge SV, which is incident to V, and there's another edge VT, which is incident to V. We say that this pair is admissible if I were to perform a splitting off operation on this edge pair, then the edge connectivity between all pairs of vertices is still maintained. I hope this definition is clear. So essentially what it's saying is like a pair of edges is admissible if somehow I can constrain all these K XY paths, K edge disjoint XY paths, to always use the edge VT if they're using the edge SV. Okay? So that's the constraint. So it's a very nice structural result that basically if you have admissible pairs, then it's a very nice property to have in your graphs. And for any edge E, we use the symbol AE, capital AE, to denote all the edges which are admissible with this edge. So which means this, if you were to perform a splitting off operation with E and F, then the resulting graph still has still maintains edge connectivity. So here's the technical lemma due to Bang-Jensen et al. From 1999. This is an extension of Loesch's splitting off theorem, because in Loesch's splitting off theorem, the result says that there exists an admissible partner for every edge under certain mild assumptions. What these people do, Bang-Jensen et al., that they give a more quantitative version of that result. So here's the lemma. So let K be an even integer and G be a multigraph on the vertex set capital V plus little v, such that for all vertices in capital V, we have edge connectivity of at least K. And further assume that degree of V is even. Then the number of admissible partners for any edge UV is at least half of the degree of vertex V. So if V had degree 8, and I'm looking at any edge incident to V, then it has at least 4 admissible partners. So more than a majority, so majority of the edges are admissible in comparison to inadmissible edges. Okay? So this is the technical result that we need for our result. But when we apply it to our setting, it's actually very simple. The resulting statement is actually quite simple. So in our setting, we have a 4 regular 4 edge connected graph, and consider any edge that is incident to V. Let's call it Vx. Okay. If you look at the number of admissible partners of E, then it is at least 2, because the vertex V, any vertex in this graph G, has degree 4. So that's why you have at least 2 admissible partners. And if furthermore, if E comma F is an admissible pair for some F that is incident to this vertex V, then the remaining 2 edges in delta V minus E comma F, they are also admissible. Okay? To see this, observe that like if you were to perform a splitting off operation with E and F, so you remove these 2 edges EF and like apply a shortcut. In the resulting graph, the vertex V will have degree 2. So it is still like it satisfies the hypothesis of this lemma. So which means the remaining 2 edges must be admissible because they are the only 2 edges which are incident to V. Any questions so far? So now our proof is actually quite simple. So what we do is, again, our goal is to obtain this convex combination for this uniform vector. We proceed by induction. In the base case, we just have like 2 vertices and 4 parallel edges. We are allowed to use these 3 green edges. And observe that this is a convex combination. This is the required convex combination. So this case is easy. In the inductive step, we are in the general case. And we have like 4 possible subcases that can happen if you were to look at the neighborhood of V. Yeah. Either V has these 3 distinct neighbors, or one of the neighbors Z coincides with U, or it can happen that the neighbors X and Y coincide, or it can happen that X and Y coincide and U and Z coincide. So these are like the 4, if we can argue that these are the only 4 subcases that can arise. And by using lemma 8, we can actually argue that in these 3 cases, in these 3 easy cases, the set of admissible partners of the pink edge is always Vx comma Vy. Yeah. And in this case, in the first case, this set of admissible partners can either have cardinality 2 or 3. Without loss of generality, we'll assume that Vx and Vy always belong to E. Okay? That is how, if some edge is inadmissible, if Vz is some edge is inadmissible, then we'll label it as the endpoint as Z. So now we have like 2 possibilities for performing a complete splitting off. So either we can split off UV and Vx first, and then split off YV and Vz, or we split off UV and Vy, followed by splitting off XV and Vz. Okay, so these are the 2 splitting offs. And this gives us like 2 branches. And yeah, so here I've drawn like what happens in each of these 2 branches. So, and what we do is like, so when we obtain these subinstances, observe that we have performed the complete splitting off. So we have 1 fewer vertex now. So both of these subinstances are on n-1 vertices. We designate the edge Ux as E1 in this case, in the left case, and for the right case, we designate Uy as the designated edge. We apply induction on both of these subinstances with the designated edge Ei and obtain convex combinations. So the convex combination for the subinstance on the left is for 2/3 chi of capital E1 minus little e1. And observe that capital E1 minus little e1 is simply the entire edge set minus the edges which were incident to V, plus this new dummy edge YZ. Okay, so we have a convex combination for this. And on the right-hand side, we have a convex combination for E minus delta V plus the dummy edge XZ. So I've highlighted the dummy edges in blue. And we just like lift these solutions back to our original graph. Observe that like in these graphs, V has been deleted. So if I want to lift these solutions back, I better have connectivity for V. Yeah. So what we do here is, so to lift a subgraph from this subinstance, we do the following. So depending on whether the subgraph contains the dummy edge YZ or not, we have a different like lift operation. Okay? So if the dummy edge belongs to your subgraph, then it must be removed because it does not belong to the original graph. You're not allowed to use edges that don't belong to your graph. So what we do in this case is we just like subdivide the edge at V. Okay? So imagine you had this dummy edge in your subgraph. So I just add the vertex V here. That is what this operation is doing. And if this dummy edge does not belong to your subgraph, you can't just like not lift this subgraph because we still need connectivity for V because V was deleted. So you want V to be 2 edge connected to the remaining graph. So what we do in this case is imagine that I add a dummy edge XY. This still preserves 2 edge connectivity. And then I subdivide it at V. Okay, so I delete this and then subdivide at V. So the reason I went through this hoop is just to convince you that like these two lifts ensure that 2 edge connectivity is maintained. Okay? So by doing this, so this is the lift operation, and we can argue just by doing some simple arithmetic that the convex combinations that you obtain are actually for this almost uniform vector that we are interested in. Plus, there's a slight bias. Okay, so the edge Vy is overrepresented and the edge Vx is underrepresented. This happens because by induction, this happens 2/3 of the times. Okay, which means Vz appears 2/3 of the times, Vy appears 2/3 of the times. And this happens 1/3 of the times, which means Vx happens 1/3 of the times and Vy happens 1/3 of the times. So basically Vy is always present and Vx is not present 1/3 of the times. That's what is happening. So the in some sense, like the error term is this, okay? And if we do a symmetric operation on the other branch, we basically get this. So we get a convex combination for, again, the almost uniform vector, but the error term is now the negation of like what was from the first branch. And so if you just use a simple average, you take these convex combinations and just do a simple average, then we get the required convex combination. So that's it. Like that's how you would obtain a convex combination for the original graph. Okay. Any questions so far? Yeah. So now let's discuss the algorithmic version, because so far, like we just gave a simpler proof of Carr and Ravi's theorem. So we still need to design a polytime algorithm. And so essentially, like we can't be recursing on 2 subinstances with size n-1 with n-1 vertices, because if we explore the entire recursion tree, then we'll have 2 to the n instances to solve. So this is clearly like not efficient. So we want to prove theorem 3. This is the algorithmic version that we are interested in proving. And again, the proof is by induction / recursion. Okay, so what we do is in the base case, again, we have like a graph on 2 vertices with 4 edges. And we always want to exclude this pink edge. Okay? And we have 3 remaining edges, green edges. And if you pick the 2 cheapest green edges, then that satisfies this property. So it has small cost. Okay? So the base case is easy. For the general case, our idea is to recurse on the cheaper branch. Okay. So what do I mean by cheaper branch? If we go back to the previous slide, observe that the theorem is telling us that the convex combination that comes from the left side is this, the right side is this. So they both are the same here. The difference is here. Yeah. So just by like the usual method of conditional expectation, if I were to just randomly toss a coin and visit one of the branches, in expectation, I'll be getting this. But if I want to deterministically go to the cheaper instance, then I should be going to this instance if cost of Vx is at least cost of Vy. Otherwise, I should go to this branch. That's it. Like it's just, we are de-randomizing this algorithm by using the method of conditional expectations. Okay? So what we do is, so our idea is to recurse on the cheapest branch. There are some technicalities involved, which we'll see on the following slide. So what we do now is we compute the set of admissible partners of the edge E, and this takes order and time. And this can be done using max flow computations. I won't get to this, but it's a straightforward exercise to do this. And this can be done in order and time, because observe that a regular 4-edge connected graph, the number of edges in this graph is 2n. Okay, so even if you were to run like a flow augmentation step, then it only takes like linear time. And to test that your splitting off operation is valid, like you only have to test if 4-edge connectivity is preserved. So all of this can be done in like linear time. And so we compute AE, and then what we do is we label the most expensive edge in AE as VX. That's what we label it as. And we let VY be any other edge, any other admissible partner of this edge E. Okay. Now, what do we do now? So we recurse on the left subinstance, the one where we performed a splitting off on E and VX. So we shortcutted it this way, and then we applied a splitting off on YV and VZ. So we obtained a shortcut edge here, YZ. Okay, so that's the operation that we did. And observe that like now we have obtained this other subinstance, which does not have some edges, which is okay, but we have a new dummy edge YZ. And if we want to recursively solve this problem, then we need to assign some cost to YZ. And for now, we just leave it as a variable. So as we go through rest of the proof, it will be clear what choice of cost on YZ makes sense. Okay. Now let's say H hat be the recursive 2H connected subgraph, which satisfies the following bound. So the cost of H hat is at most 2/3 times the cost of this graph minus the designated edge, which is essentially basically G minus V. You have the edge UX and the dummy edge YZ, but you're allowed to ignore the designated edge. Okay. So the expression just simplifies to 2/3 the cost of G minus E, and there is this additional term. Okay. And this is the cost arising from the dummy edge. So let's see how we finish the proof of theorem 3. So what happens here is, so there is one last hurdle that we need to solve. Recall that when we obtain a subgraph for the subinstance, and now we want to like lift it back to the original instance, there are two possibilities. Okay, so it's not always like a deterministic procedure. So it depends on, or more like it's not, we don't always have a control on whether the dummy edge belongs to the subgraph or not. Okay, so depending on its cost, it might be wise to actually include it in the solution or not include it in the solution. So the lift of H hat, which we define as H, is defined again the same way as we saw in the existence proof earlier. So what we do here is if YZ is present, then we just subdivide this edge at B. And if YZ is not present, then we add the dummy edge XY and then subdivide it at B. Okay, just the same operation as before. Now, if you are doing a worst case analysis, then we need to control the cost in both cases. Okay. So here now we define the cost in this particular way. So where is this expression coming from? So observe that when we perform this lift, the edge Vy is always present. So the variability only comes from these three edges, and these two edges are already, they have like a fixed cost, and this is the variable cost that we have some control on. Okay, so if we can define so if we set the cost of YZ of this dummy edge to be the cost of VZ minus the cost of VX, then we can see that in both cases, increase in cost equals the cost of Vx plus the cost of Vy. Okay? So if the dummy edge is present, then you save on the cost of Yz, and then you pay for Pz. Okay? That's the intuition. Observe that like the cost of this dummy edge can possibly be negative, but this is okay because in theorem 3, when we stated it, like we clearly said any cost function is allowed. So this is one of the advantages of our result. The result works for even arbitrary cost functions, and this is actually used in our algorithm. So just like doing the final calculations, so the cost of our lifted subgraph H is the cost of the recursive solution H hat plus the increase is always CVX plus CVY. And if you just do the arithmetic, like just write down the entire thing, then you'll see that the cost is 2/3 the cost of G minus E. This is the budget we had. And then there is this additional term. And now recall that we chose CVX to be at least CVY. So we applied a splitting off operation on the, we chose Vx to be the most expensive admissible partner of the pink edge E, okay? Yeah, that finishes the proof of this main theorem. Okay? Let me just, on this like last slide, I'll just give a formal proof of theorem 3, okay? The 4/3 approximation algorithm that we claimed in theorem 1 for 2 ECM on half integral instances. Okay? So in this, we are given a half integral instance of 2 ECM, which means like we are also given an optimal half integral solution to this LP, okay? The same subtour LP or the 2 ECM LP. We construct the graph GVE where the vertex set is the same and the edge set has 2 times XE copies of the edge E. Okay? So intuitively, the way you should see this is that the cost of E is like 2 times C transpose H. That's what is happening here. Okay? And we overload the same cost function. So the edges in G, the cost of these edges is just derived from the cost of these edges in G bar. Okay? And as mentioned before, like G is 4 regular 4 edge connected by the same reasoning as before. We then apply theorem 3, which shows how to obtain a 2 edge connected spanning subgraph H such that its cost is bounded by 2/3 the cost of G minus E. So you have the entire budget of like the graph without the edge E, and that times a 2/3. That times 2/3. That's the budget you have, and we gave a order n squared algorithm for doing that. And we just translate the solution H back to the original graph. So the vertex set is the same. What we do is for every edge that appears in H, we use the same edge in G bar. That is all we do. Okay? And as mentioned before, like because G is induced from 2x, we lose a factor 2. So this 2/3 and then this factor 2, that results in the 4/3 guarantee. That's what gives the 4/3 number. Let me just quickly wrap up the talk by summarizing the results that we saw. So alpha 2 ECM denotes the integrality gap of 2 ECM LP, and the same for TSP. So we saw a simpler proof of Carr and Ravi's result. So what we showed is that the integrality gap of what Carr and Ravi showed is that the integrality gap of 2 ECM in half integral case is at most 4/3, and we gave a simpler proof for it. We also gave a matching approximation algorithm for this problem for 2 ECM on half integral instances. So the very first natural question is, can we obtain an efficient algorithm for finding the convex combination? Because observe this, like even though I say that like we gave the algorithmic version of Carr and Ravi's result, it's not like a full answer, right? Because what their theorem says is that like there is a convex combination, and what we are doing is we are identifying a two-edge connected subgraph which beats this the average of this convex combination. Okay? A full result would actually like give an efficient algorithm for obtaining the entire convex combination. There are some hurdles in doing that, but it seems like a reasonable open problem to look at. Then remember that, like I was saying, the motivation for studying half integral instances is that they're known to be the hardest, like they're believed to be the hardest instances for TSP. And we know that half integral instances for TSP, they give a lower bound of 2/3 for the integral. That might not be the case for 2ECM actually. So what Alexander Boyd and Elliott Magwood showed is that the integrality gap of 2ECM on something called as half triangle points is at least 6/5. Okay? So what these half triangle points are, they are a subclass of half integer points with the further restriction that if you look at all the half edges in this solution, then they form vertex disjoint triangles. So that's what like half triangle points are. So what these authors did is they gave an infinite family of instances where the integrality gap of 2ECM is at least 6/5. And in a follow-up work, Boyd and Lego showed that the integrality gap for this class of subinstances, for these class of instances, is actually upper bounded by 6/5. Okay, again, this is just some sort of a constructive result. Okay? This is not polytime, so this is still open to. This is an open problem. Polytime not known. Okay? So if I were to summarize these results for 2ECM on half integral instances, if I were to look at the integrality gap, we know that it is at most 4/3, and we know that it is at least 6/5. And we know that the integrality gap for TSP on half integral instances is at least 4/3. So a few questions are like very natural to ask. So the first one is there a gap between these two? Okay, that would be a nice question to answer. Right? And then the second is which would be like stronger than like what we asked regarding the gap, is that like, is this a strict inequality? Okay. If you show that it is strict, then we already know that there's a gap. Okay. And the most like far-reaching like conjecture, like this, I think Boyd and Lego conjectured this, I think Alexander Boyd and Elliott Magwood conjectured this. They conjectured that this is actually tight. So is this the true answer for the integrality gap of 2ECM on half integral instances, or maybe like even for general instances? And the last question that I would like to motivate is like, can we say something about the integrality gaps for the general problem, like not focusing on like special instances? Most of the times, like all results that we know are basically like the results for TSP, which just carry over to 2ECM. But because like 2ECM is in some sense like easier to work with, I think like we should like have results that are independent of TSP, like some stronger results for TSP. So that's the last question that I would like to motivate. Thank you for your attention.
All right, if everyone could please unmute and let's give the speaker a hand here.
Thank you.
Okay, any questions for Sharat?
Do you have a
yeah. Sorry, go ahead. Go ahead, Cedric.
Sorry. Do you have a tight example for your algorithm?
So the thing, no, the answer is no. And the thing is, it might be the case that, so your question is like, is our You're not asking if the integrality gap is 4/3, right? You're just asking if our algorithm like can.
Yeah. Do you have family of
we,
instances where your algorithm actually gives a 4/3?
Okay. No, I can't think of any such thing. But thanks for mentioning it, because I haven't really, that never came to my mind. Probably it's a good idea to see if such a thing can be shown. Yeah.
So I had a question. So actually more a comment. So with regard to your question 1 on efficient algorithms, I'm wondering why the Carve-Impala method doesn't work. So it's not the Carve-Impala paper that you're quoting, but they have another paper there where they basically show that if you have an alpha approximation with respect to the LP, then you can use it to to show that like alpha times a fractional solution dominates a convex combination, and find the convex combination. And it just uses the ellipsoid method. It's quite simple. I mean, you just, the variables are the multipliers that you put on the solutions. This is a fairly well-known thing.
Oh, I see. I wasn't up, because I see that like a lot of work goes into actually finding the convex combination as well. So maybe I might have to double check if that's what they do. I know that like they show it as an existence result, that if the integrality.
Well, so the idea is very simple, right? I mean, you use the multipliers in the convex combination as your variables, and so you write an LP saying that I want to find a convex combination that is at least 4/3 x. That has an exponential number of variables, but then when you go to the dual, the separation oracle becomes is something that you can, for which you can use your approximation algorithm.
I see.
There's this paper by Carve-Impala called Randomized Meta-Rounding that talks about it, and it's been used also in other contexts in mechanism design. So, I mean, I have a paper with Ron Levy that shows how to use it. So,
yeah, thanks for mentioning it. Actually, like I'll take a look. Yeah, because that would be, that would like essentially resolve this question. Just a quick question actually, because my co-authors are also here. Sylvie or Joseph, like, do you have any idea about like the result that Swami is talking about?
So I only know about the old Carve-Impala paper. You're talking about some newer paper?
Well, I mean, Carve-Impala have multiple papers, I think, but they have a paper called Randomized Meta-Rounding, which exactly states what I said, that if you have a LP relative alpha approximation, then you can use, let's say for a minimization problem, then you can use it to find a convex combination that's dominated by alpha times a fractional solution.
Right. I mean, there's lots of results that kind of show those things are all equivalent in different ways, right? Some of it goes back to Goemans as well. So, yeah, but I wasn't aware of that paper, actually. I'll have to look.
Yeah, I can send a link in the chat channel.
So yeah, Sharat, I don't know a good answer offhand, but so there must be some catch, unless I'm missing something, because you know, this problem in this particular Carr-Ravi paper has been mentioned as an open problem to find a polytime algorithm for this convex combination, right? So it's a known open problem in the area. So so what I'm wondering is, from Swami's comment, why not put the two why not put the Carr-Ravi and the Carve-Impala paper together and have an algorithm for the Carr-Ravi paper, right? So there must be some issue that I'm missing at least.
But Carve-Impala is assuming that we have access to an alpha approximation algorithm, which was not the case before. These are the ones.
Yeah.
Like,
so,
okay,
but the point is, if you have a convex combination, you can get the alpha approximation. I think that's fairly straightforward, right? And so what this other Carve-Impala paper is showing is that the other direction is also true. If you have an alpha approximation with respect to the LP, then you can use it to find the convex combination.
Okay, yeah, I agree, Swami. Yeah, that was the missing piece. Indeed, yes.
Okay.
Thanks again, Swami. So I just like to make a quick remark, like I forgot to mention this. So this is the proposition which is like gives some motivation for considering these kind of special instances. Just like to quickly highlight that Kar and Ravi's result essentially is for the case k equal to 2. So in some sense, the reason we are working with half integral instances is because they're a stepping stone to working with like more general instances. So this is the motivation. So for this eventual goal of showing that 2 ECM-LP has small integrality cup, ideally we want to work with all possible like k, and working with the smaller case first might give us ideas to deal with like larger case. Yeah, please feel free to ask other questions. Yeah.
Yeah, I mean, you mentioned like when you were stating this proposition that this is further motivation for considering half integral, but it just seems like the motivation is that, I mean, the tight examples that we know of are coming from half integral solutions.
Sure, but that only says that we just believe that like these are probably like the hardest instances. But what this says is that it also gives you a roadmap. Like, so it says that if you start working with like 2k regular, 2k edge connected cuffs, as you keep increasing k, like you're closer to actually proving the statement for the general case.
No, I get that. But I mean, the half integral is basically k equal to 2, right? So
yeah.
I mean, I guess the conjecture is saying that you only need to work with k equal to 2. And I mean, this proposition is not saying anything about that. This proposition, with respect to this proposition, half integral is just saying that, okay, k is equal to 2.
Yes.
So I don't see why this proposition is kind of giving motivation for focusing on half integral solutions.
Because it's the simplest case that arises in some sense. Like, or the graph induced by half integral solutions are 4 regular, 4 edge connected. So, but maybe we might never show that like half integral instances are the hardest instances. Maybe that's not the case. But if we can still show this, then this is like trying to make progress, like partial progress in the problem, if we can go via this route.
So can you sort of sketch, like highlight, like what goes wrong with the next case? For instance, k equal to 3, like where do the techniques break down?
Yeah. Okay, so the biggest problem is in making these arguments work is that the statement that we have here, theorem 2, where we obtain a convex combination for chi of for this uniform vector. So if you were to try to just produce a convex combination for the uniform vector, also including the edge E, it's very difficult to make the argument work in some sense. More like, I know it's an easier problem, but the thing is, somehow excluding that this edge from all 2 edge connected subgraphs makes the proof go through like in an easier way. So for the more general case, when you're working with 6 regular 6 edge connected graphs, we need a good hypothesis. Like again, like what are the assumptions? Like how will our subgraphs look like? And if I were to like mention the lifting operation, let me just quickly mention this. So observe that here, if the dummy edge is present, then we do something. If it is not present, we do something. If the edge E1 were also like, if we were allowed to also use this edge, then we might have to come up with a more like nuanced lifting operation. Because if edge YZ is not present, then we include Vx and Vy. And if edge ux is present, then we might have to subdivide at v, which means we get vx and vu. Now we have two copies of the edge vx, which is bad, like, because whenever we have two copies of an edge, we might have to like, we might start like collecting many more copies of the edges. So like, even though I didn't make it explicit, but the way this theorem 2 is stated in Karavi's paper, it is actually important like to work with these kind of assumptions. When there are like many more dummy edges that can be present in your solution, it's unclear, like at least it's how one would like lift these solutions back up. We might end up like having more than one copy of an edge in these recursive solutions. And when you're like lifting them up, like for each dummy edge that is present, like you will have to subdivide in some sense just to preserve the structure. And if you have more than one copy, then you will like continue having more than one copy in your lifts. So the cost analysis becomes much harder to make work for the cost analysis to go through. So that's the issue. But I do think that maybe like more like Bang-Jensen et al.'s lemma, it actually says that we have a lot of admissible partners. So maybe this aspect of is still like good. So we know that for any edge that we are trying to split off, like there are lots of admissible partners. Maybe we can iterate through a lot of combinations just to construct like an unbiased convex, we can iterate through a lot of complete splitting of operations so that the average of all of those ends up being the vector, the uniform vector that we are looking for. But it's unclear like how the lift is going to work. I would say like lifting is the main hurdle.
I have a comment on that as well. So if you go to 6 regular 6 edge to connect it, and even if you have the one edge missing and you use the nice result that says there's 3 ways to split off, the problem is the fraction that you're looking for is smaller than 2/3. And so the edge is missing more of the time, and that makes the numbers not work out. So whenever it's missing, you have to add edges in when you lift. And it so ends up costing too much.
Mm-hmm. I mean, it seems that for k equal to 3, maybe you need to exclude 2 edges. I mean, I'm thinking of the Ravi thing, and if you exclude 2.
Yes, I agree. Exclude 2 edges, but then it gets pretty tricky.
Yeah, I can imagine that, yeah.
They might not be together.
Any other questions?
Okay, it looks like there's no other questions. So let's thank our speaker again.